I will try to move quickly through this talk. This is an outline of what I would like to talk about. First of all, just to outline the planetary energy budget. To understand Earth's climate, a great deal of understanding can be obtained just by looking at the energy budget of the planet. Then I will move quickly into data just to show you observations of data from remote sensing and in situ measurements from all around the world. And then I will, obviously the connection with fossil fuel burning is so obvious, but I do want to summarize some of the data and then at the end say a few words about climate research. This slide is obviously just a cartoon, but it sketches the exact number that Professor Santamaria mentioned. Although he used the number 342 watts per square meter, I have the number 341 watts per square meter. There's been a recent calibration which I'm convinced of. At any rate, to a first approximation, the Earth is in balance. The Earth receives visible energy from the sun and radiates infrared to space because of the temperatures of the black body of the sun and the black body of the Earth. About 30% of the incoming sunlight is directly reflected, so that the amount absorbed is 239 and the amount emitted is roughly 239. However, the presence of greenhouse gases in the air causes the radiative transfer to be more complicated, and there is a net warming on the surface of the Earth exerted by the downward radiation from the greenhouse gases. The radiative transfer calculation is really quite interesting. But Professor Santamaria mentioned that you can balance the two incoming energy and the outgoing energy and solve the equation for the effective temperature of the Earth. And when you do this, you obtain an incorrect answer, that the Earth is freezing everywhere, minus 18 degrees centigrade. And the reason for the error in the calculation is that it has ignored the greenhouse effect and the presence of clouds. For the planet Mars, we can calculate the temperature of the surface very accurately. There is a very thin atmosphere on Mars, very low pressure. But for Venus, we also underestimate the temperature very badly. This is indirect evidence for the reality of the greenhouse effect. And I will also mention one other kind of evidence for the reality of the greenhouse effect. One of the first scientific instruments that ever orbited the Earth looked down on the Earth to observe infrared emission of the planet. And if the planet were emitting as a perfect black body curve at the temperature of the tropical Pacific Ocean, the temperature would be 27 centigrade or 300 Kelvin. But instead of that smooth curve, what the satellite actually observed was this curve, showing again this window region of wavelengths, La Ventana, at about these wavelengths where the atmosphere is mostly transparent so that you can see down to the surface of the Earth, except for certain absorption features, ozone, many carbon dioxide features, many other greenhouse gases. So I'm going very quickly, but I do want to indicate that there is real evidence that the greenhouse effect is natural. But the problem we have now is that humans are enhancing and amplifying the greenhouse effect. The most common graph to see is this one of carbon dioxide measurements, so that the black dots are at Mauna Loa, Hawaii, and the red curve is at South Pole, Antarctica. This is now 50 years of data, and the Mauna Loa results are measured every hour, so that every dot is the month, an average of a month taken every hour. The underlying trend is quite large, and the fact that this carbon dioxide is from fossil fuel emissions is established by several lines of reasoning. The isotopic content, that is the carbon-14 and carbon-13 content of the CO2. The geographical patterns, the amount of the increase is within about 50% of the fossil fuel emissions. The seasonal variation, etc. There are many lines of reasoning that demonstrate that the carbon dioxide is from human activities. One other greenhouse gas, which I will summarize briefly, is nitrous oxide. The results are similar, where nitrous oxide amounts measured from all over the world are increasing, although the amount is parts per billion as opposed to parts per million. And when one examines ice cores over geologic time, one sees that the greenhouse gases were never as high as they are now. This record is from French investigators from 1998, where the present time, the current time, is time zero, 50,000 years ago, 100,000 years ago, all the way back to 450,000 years ago. The last ice age, shown by the blue temperature proxy data from isotopes of the ice, there was an ice age at about 20,000 years ago, at which time the carbon dioxide amount was 180 parts per million, and the proxy temperature was about 6 degrees centigrade lower than it is now. The previous ice age was 150,000 years ago, approximately 250,000 years ago, and so forth. And every time it was cold, the carbon dioxide amount was very low, 180 parts per million. In the warm interglacial times, such as here, the pre-industrial time, 270 parts per million, 280 parts per million, 270, 280, 280. So the natural range of carbon dioxide is between 180 and 280 parts per million. And this kind of a graph now can be extended back to 800,000 years. And the agreement between ice cores from Antarctica and Greenland is quite striking. So we are looking at globally significant data. Similarly for the greenhouse gas methane, when it was cold, the methane amounts were 300 parts per billion. When it was warm, 600. When it was cold, 300, 600, and so forth. So we have some evidence of the natural range of these greenhouse gases, and that we have exceeded those ranges now. And as I said, the carbon dioxide increase is definitely from human activities, approximately 85% from fossil fuel combustion, and approximately 15% from deforestation. The burning of the trees, of course, releases carbon dioxide, and the organic matter in forests, which are cleared, becomes oxidized and releases carbon dioxide in normal soil decay processes. This figure is not so well known, I might say. So that the net effect on the radiation, the energy budget of the Earth, is that these enhanced greenhouse gases, that is the increase in the concentration of carbon dioxide that is only due to human activities, causes a warming effect of 1.7 watts per square meter at the surface. The increase in methane due to human activities and the other greenhouse gases, a number of fluorine-containing gases, gives a total of 2.7 watts per square meter, which is more than 1% of the solar constant. And over geologic time, there is no evidence that the sun has ever varied by that amount. Of course, the evolution of stars, which astrophysicists now can study and measure, there is no stellar evolution of a star like the sun which can proceed at 1% in 50 years. The rate at which the Earth's energy budget is being changed is very rapid compared to nature. Now I want to move to the data. There are several groups around the world who are doing careful recording of the Earth's temperature. This one happens to be from the NASA Center in New York City. 0 on this graph is not 0 degrees on any scale. It's a reference level. It is taken to be the average of all the temperatures in the world over this 30-year period from 1950 to 1980. This graph represents several hundred million temperature points measured at the surface of the Earth, both air and water. From the time that thermometers were first used reliably in around 1880 through the year 2010. And you see that in the late 19th century, the temperatures were generally lower than they were in 1951 to 1980. But in many cases, the annual oscillations or swings can overlap. So this appears to be a significant change until here, but the largest change, the most significant one, is the last 30 years, where the rate of temperature increase is the largest. It is nearly monotonic, although you can see annual changes. These are annual averages. And these temperatures are definitely outside of the noise of all of these previous eras. So there is something different happening about this last 30-year period. Now, these temperatures actually exist in much detail, geographical detail, seasonal detail, month by month. So I'll show you just a little bit more. You can take those same temperatures and break them apart into northern hemisphere and southern hemisphere. So the southern hemisphere has generally warmed a little bit more steadily than the north, but the warming is slower now. The northern hemisphere is warmer than the southern hemisphere. And this is as if there is an external heating imposed on the system and the ocean warms up more slowly. The southern hemisphere is mostly ocean and the northern hemisphere is mostly land. So the northern hemisphere is warming more rapidly. Now, in 2008 and 2009, the temperature was a little bit low compared to the previous years. And in Washington and New York, many people were saying that global warming had stopped. But in fact, you will see that the highest temperature ever recorded in the southern hemisphere was the same time. So there's a great deal to learn by looking at the detail. And in the climate business, 1 year data is not enough. It takes many years of data. So the 5-year running mean, I think, tells the story. There is much more detail. For example, these are the annual surface temperature anomalies, that is the difference from the average, 1951 to 1980, for 3 years. 2010, which was the warmest year of the entire record, 2005, which was the second warmest year, and 1998, which was essentially tied for the second, with the outlines of the continents. And the false color code here is red and brown is the hottest, the most warming, and the blue is cooling. You can see that everywhere on the surface of the Earth there has been a warming. The only places where there is negligible warming is over the oceans because of the heat capacity of the water, and places where there are no data here. Everywhere else has warmed. The Arctic region is warming the most, and the centers of the continents are warming the most. This is a very physical, this is physically intuitive that this is what is happening, but we can also do the calculations. But once again, these are only data. I am only showing you actual measurements. And of course, there are month-by-month records, which I don't want to go into the detail now, but there is a great deal of detail in this record. Now, the world's ocean waters are also warming. It is more difficult to measure the ocean water temperatures statistically because we do not have cities in the oceans, we do not have regular measurements. All of the measurements are taken by ships and recently by satellite remote sensing. But when oceanographers have taken all of the data available over the last 50 or 60 years, they measure it in terms of heat content of the upper waters of the ocean. The upper waters of the ocean are in contact with the atmosphere. The deeper ocean is not in contact with the atmosphere, so we do not expect to see any warming. But if you take only the top 500 meters or 600 meters of water, the trend line is that there is increasing heat content of about 4 times 10 to the 21 joules per year heat content in the upper oceans. And that is about 1/10 of the enhanced greenhouse effect. So some of the warming in the air is not being observed yet because the heat is piling into the oceans, of course. Now, sea level. For a long time, about 100 years, people were measuring sea level rise around the world very carefully, but in a very primitive way, with very old-fashioned instruments, by pounding rods into the seashore and recording where the water level comes to the rod at many places around the world, and recording the average sea level. And by doing those measurements very carefully at a number of places around the world, a sea level rise was observed for 100 years about 15 centimeters, 16 centimeters. The red part of the curve from 1992, the red part of the curve represents new instruments, remote sensing instruments on satellites, radar ranging devices, and LiDAR ranging devices. And those data are obtaining a much better measure of sea level rise. There's more sampling, more often, more accuracy, and more precision. And even though this red curve looks like it agrees with the early one, actually the new rate of sea level rise is double, 2 times as much. So instead of 1.6 millimeters per year, it is now 3.2 or 3.3 millimeters per year since 1992. So at first, when this new rate of sea level rise was observed, we thought that it might not be different from this one, but we need enough. But now, after 18 years, it's very clear that the sea level rise has doubled in its rate in the last few years. Now, another kind of measurement has to do with the amount of ice that is sitting on the continent of Greenland. This measurement is made by satellite sensing of the Earth's gravitational field and the extremely small departures from a spherical gravitational field around the Earth. So the instrument is really beautiful. It's a very high-tech instrument, and it's been flying now since 2002. 2 satellites go around the Earth, and when the first satellite experiences strong gravity, such as a mountain range, it feels a little bit more acceleration, and the position of that satellite is linked to the second satellite very carefully, so that when the second satellite comes to the same place, it can repeat all the observations, so they can map out the Earth's gravitational field very well. But if the gravitational force is changing with time, for example, due to a glacier growing bigger or smaller, eventually, after a number of orbits, the rate of change can be measured. In fact, these satellites have now been able to measure the change in the water in the Indian subcontinent below the surface in the season when it is drawn down. It's amazingly beautiful work in the field of geodesy. Well, what these data show after 7.5 years is that the mass of ice on the Greenland continent is not only decreasing, but the best fit to the curve is an acceleration, not a straight line. And the median, or the mean amount of loss is 240 billion tons per year, and that equates to about 0.7 millimeters per year sea level rise. And that is the average over this period. The current rate is a little bit more than that. Similarly, Antarctica. The same kind of measurement is now being made over Antarctica. Now, in the first part, when these authors first published, the primary author is Isabella Velaconia. She's a physicist in my home department at UC Irvine. Her co-author was John Vare. But when they first published these data, we could only see the first 3 years. And it was clear that the mass of ice is decreasing, but the acceleration has now become clear after 7 or 8 years. So it's very difficult to predict what will happen to the accumulation of snow and ice over Greenland and Antarctica. It's much more important to measure it. And Another independent instrument has been measuring the height of the ice over Greenland and Antarctica, and they also deduce an accelerated decrease in the mass of ice over Greenland and Antarctica. So this is quite real and quite serious. Unfortunately, we really cannot predict how this will continue in the future. There's not enough understanding of the mechanics of the ice and the delivery of heat from the ocean circulation to the ice shelf surrounding the continent. But if you simply extrapolate these trends, then we will have at least 1 meter of sea level rise in this century, perhaps 2 meters. Now, many of you have heard that the sea ice floating on the Arctic is decreasing. This is more dramatic, and this is what the general public can see. They can see that the sea ice is disappearing on the Arctic, and we now have ships navigating across the Arctic in the summertime. This band of data is a 30-year average of the sea ice extent on the Arctic in the summer months, June, July, August, September, and so forth, over a 30-year average. And this is the last 4 years, 2007, 8, 9, and 10. They are all well below, what is that, about 40% less sea ice in the summertime now. And you can see that at this date is when the freeze normally begins, so that the sea ice begins to increase every year. That date is now becoming later because the open ice allows sunlight to be absorbed by the Arctic Ocean. It warms up a little bit more in the summertime, so this is at least one factor in trying to predict whether we will have no ice in the Arctic Sea in the coming decades, because the water is being warmed by sunlight over a longer period of time in the summer. Now, there are other forces at play, but these kind of data are now becoming available. Now, those data tell us that climate is changing, perhaps accelerating, but I want to remind you that this is not a mystery. We understand the physical principles. It is quite simply the greenhouse effect of the enhanced amounts of greenhouse gases. I'll show you one model calculation result. This is from a British group where they tried to simulate the temperature record of the average surface temperature, and this noisy record are their simulations, and the black curve is the data. And you can see that they really were not able to simulate the actual temperature record unless they included the greenhouse gases and the climate forcing of them. So this is another kind of evidence that, again, the climate changes that are being observed can be explained by the greenhouse gases. Now, a few years ago, I was certainly thinking that perhaps the sun itself is causing the change. And I said to you earlier that this temperature record of the last 30 years is distinctive. There's something special about this last 30 years. The rise is more or less continuous. These data do not fall within the noise of the previous 100 years. But there is one other special feature of the last 30 years. It is the first time that humans have been able to measure the output of the sun. These are very precise measurements of the total solar irradiance that have been made now by several satellites, not continuously, but Klaus Freilich in Switzerland and Judith Lean, she's at the United States Navy actually, she's a physicist. They have strung together several satellite records, and this is the record of total solar irradiance that they have been able to reconstruct for the last 30 years. And you see that the sun is not releasing more energy. It is nearly a perfect 11-year cycle, just like the sunspots are roughly an 11-year cycle. Now, this last solar minimum was very pronounced. The recent data are back to about here, I should say. But the last solar minimum was very low. Other than that, this is rather a strong oscillation. So, as I say, 10 years ago, we were theorizing that the sun was causing the warming. Now this is no longer tenable. We have evidence that the sun is not causing the warming. So we have evidence that the greenhouse gases do give the right warming, and that the sun cannot possibly be giving the warming, there are no other good ideas. Now, we can always think of some wild theory, but these are the best. Now, in the meantime, the world's energy demand is increasing. If you look at the global fossil fuel carbon dioxide emissions, it's almost ridiculous to go back to the year 1750, but that's what I have on this graph. It's from some colleagues at the Oak Ridge Laboratory. Until the middle of the 20th century, the global carbon dioxide emissions were about 1 billion or 2 billion tons of carbon as carbon dioxide. Now the annual emissions are 8 billion tons of carbon as carbon dioxide because of worldwide fossil fuel energy usage. So that whatever is happening on climate, as measured in temperature, ice amounts, and so forth, we do expect it to continue and to accelerate because the principal driving force, carbon dioxide, the emissions continue to grow. This graph is from some United States Department of Energy people. It's a relatively independent group here that they're independent scientists. And obviously, these are historical data on the worldwide energy usage from 1990, 95, 2000. These are historical data, and in the future projections. In 1970, the energy usage was 207 of these units. These are terrible units, quadrillion BTU. They're not good scientific units, but they're okay. 207 in the year 1970. That had doubled by the year 2000. There will be another 75% growth by the year 2030 or 2035. But the difference is that most of this demand was by the developed, advanced countries who were using energy rapidly, like the United States and Canada, Japan, Western Europe. Most of this growth in the future is due to energy demand in developing countries, emerging markets. So in trying to obtain an agreement amongst the world, the nations of the world, we have the developing countries saying that you people caused all of the problem, and then the advanced countries are saying, oh, but this growth in the future is due to the developing countries. So it's a difficult political problem. Now, I have one last slide I want to show. It's a cartoon from some Japanese colleagues. One of the things that the countries of the world is trying to avoid is a dangerous accumulation of carbon dioxide, whatever that is. We cannot really define yet what is dangerous. But the cartoon is a bathtub, obviously. Now, I can write differential equations and make the same point, but the input when this cartoon was made was 7 billion tons of carbon in the form of carbon dioxide per year. Now it's 8, and then deforestation takes it to about 10, but call it 7. The drain is the natural absorption capacity of the Earth. 3 billion tons of carbon in the form of carbon dioxide. About 2 billion tons per year go into the ocean. About 1 billion tons per year go into enhanced growth on green plants, mostly on land, mostly the growth of forests again, and sequestration of organic matter in soils. But the point is, these measurements have been, these estimates have been obtained after about 30 years of measurements of oceanographers and of terrestrial ecologists. Now there is a new way to assess and to estimate this absorption capacity. It's by measuring atmospheric oxygen to better than 1 part per million. And I will not show the data today, but they confirm that the natural absorption capacity of the planet is about 3 billion tons a year or a little bit less. So the imbalance we have is from an atmospheric point of view, we are adding 8 billion tons a year of carbon as carbon dioxide and can only absorb 3, so the level of atmospheric carbon dioxide continues to rise. Now, you've heard these political targets of reducing emissions by 2/3. This is not a random number. It's the number that is dictated by this imbalance. The absorption is only about 1/3 or 40% of the emission of carbon dioxide. So if we have the goal of maintaining a constant level of atmospheric carbon dioxide, you might think that intuitively all we have to do is to hold the emissions of carbon dioxide constant. It's not true. They must be reduced by about 2/3 if we want to hold the mole fraction, the concentration of carbon dioxide constant in the atmosphere. This is an enormous challenge because of our demand for fossil fuels. Now, given that some of this is going to continue, I think this is my last slide. Many of you will remember the extreme heat wave in West Central Europe in July of 2003, especially in Paris, when there was a very large number of extra mortality in Paris in that month, perhaps 10,000 or 12,000 people. This graph shows an actual temperature record, the yellow, recorded in that geographical box surrounding Paris every July of all these years. This was the average July temperature in 2003 in Paris. It was approximately 1 in 300 year statistics, several standard deviations away from the average. Now, assuming a continued warming of the type that will come from these greenhouse gases, by the year 2040, that kind of temperature in July will be average, 1 out of 2 year event, 50-50 in Paris. So it shows the need for adaptation to climate change, that we try to limit it, we try to prevent it, but there will be further climate change. So what that means with respect to mortality of old people in Paris is obviously better hydration, more air conditioning, taking care of the vulnerable people. This is just one example. This calculation is also from the UK group, Stad et al. But it makes the point that even though we cannot make predictions yet in the small geographical region that we want, say half of Spain or the state of California in the US, we cannot make predictions that are good yet. If you simply look at the data and their normal statistics and the way that the average temperature is rising, you can get a feeling that this is serious. So I will close with this final slide showing that for many years, we regarded the absorption of carbon dioxide by the oceans as something good. This is preventing further climate change. It is slowing down the increase of carbon dioxide in the oceans. But in fact, the oceans are acidifying now due to the extra uptake of carbon dioxide in the ocean carbonate system. So the red curve is simply a very simple prediction. In equilibrium with atmospheric carbon dioxide concentrations, what will happen to the world's average ocean pH, which now is about 8.1 or 8.0, but it has probably already fallen by about 1/10 of a pH unit. And as carbon dioxide proceeds along this doubling, the ocean pH will almost certainly change by about 3/10 of a pH unit. And the biological oceanography is very much a mystery at this point. It is not clear what kinds of adaptation and what kind of sensitivity there is on many marine species. So there is much need for research on the climate, not only the temperatures and be able to predict them and to understand all the other things that influence them, but the rate of sea level rise is now not predictable. We can only extrapolate. One of the most important variables which scientists are just now learning how to predict are the precipitation amounts as a function of season. And we are seeing the difference now. Precipitation is falling in more extreme events. There are more intense events being recorded compared to the historical statistics on every continent. So the frequency of extreme events is something that everyone is trying to understand, but I would say that our level of understanding right now is not very good. And then, of course, the large challenge of how to limit carbon dioxide emissions from fossil fuel burning by obtaining better energy efficiency, by using more renewable energy as opposed to fossil fuels, by learning how to work with nuclear power more successfully, and perhaps by carbon sequestration, geological carbon sequestration, if possible. It certainly will not work everywhere, but perhaps there are some geological regions where it can be done. So if I may, I will stop here and thank you very much for permitting me to speak.